Thank you very much for the introduction. Thank you very much for being still there. So I will present 3 different methods that probably you use already, but sometimes it's helpful to make distinction between different methods and compare them. And also sometimes you use some methods and you are not actually aware of the geometry you're using, so it's perhaps also helpful to put a framework around it. So I will be interested in this talk about shape spaces, mainly of curves and surfaces. So there are 2 objects. There is something which is called a prey shape, which are shapes but with a parameterization. So parameterize a curve in this example here. So you can parameterize, as I said before, a curve with a different parameterization. So this corresponds to different colors for this on the same curve. The shape space will be the unparameterized curve in this case. So in blue, for instance, you have a arc length parameterization, and other colors represent different parameterization. So this shape spaces are coming with a fiber bundle structure. So downstairs you have a quotient space by the group, the quotient of the group of parameterized shapes by the diffeomorphism group of your model. You have seen this picture before. That's for surfaces. So here you look at parameterized surfaces modulo parameterization, which gives you a genus 0 surface. In this case, if you start with a parameterization by the sphere, the 2 sphere. You probably know that shape spaces are nonlinear manifolds. What does it mean? It means that if you start with an arbitrary parameterization of ballerina here, and compute and interpolate linearly between this red one and this other one, you compute linearly, meaning that you deform your ballerina from this shape to the end shape here, just by moving linearly the points. And of course, it gives you very bad results if your parameterization is bad. The bottom line is the same procedure, but if you start with arc length parameterization on the left and arc length parameterization on the right, it's a bit better in this example, but still you see unnatural things happening. So the very large application of this talk is mainly action groups on shapes. The group can be almost everything, so you can look at the group of translation. It should be R2 here. So this group acts on shapes. So here are elements of the same orbit. So if you want to do analysis on shapes, you can also have a normalization step, which is equivalent to distinguish a particular element of your orbit. So for instance, you can distinguish the shape that is where the mean is center at the origin. So the center of mass is center at the origin. Or you can prefer to start your shape with a distinguished point at 0, 0. That's another possibility. So these are, as I said, orbits by the group of reparameterization. You can also look at the group. So is SO2 again acting in this 2-dimensional case by rotation, and you can think of your shape space as spaces of orbits. So here are elements of the same orbits, or you can normalize your shapes by, for instance, orienting the principal axis of your shape with the axis of the grid of a given orthonormal frame, or you can start with a tangent vector horizontal, for instance. That's different ways to normalize. You can look at action by rescaling and choose a preferred element of an orbit by imposing length 1 of the parameterized curve. Or you can choose a curve such that the enclosed area is equal to 1. And this different choice will have a lot of consequences in your analysis. So for instance, if you think of a fractal curve, it will look very differently if you renormalize a fractal curve with length 1. It will be very small. The shape that we will get will be really small. Whereas if you renormalize by imposing enclosed area equal to 1, it will have a different size and probably more closer visually, actually, to a smooth version of it. So the main message in this talk is to it's to be aware what you're doing in your applications. So if you make a normalization choice, if you have to know that it has consequences, and you can also think of what are the best choices to do with respect to application. So in my talk, I will concentrate on the action of the diffeomorphism group. So here my parameter space will always be 0, 1. So the curves are parameterized by 0, 1. And the group of reparameterization, so is a group of strictly increasing function from 0, 1 to 0, 1, acting by reparameterization. So you can, as I presented in my previous talk, you can have different parameterization of the same shape. Arc length is an example, curvature length is another one, curve arc length is another one, and the clock parameterization is still another one. So you have many choices, and the best choice depends on the applications. So let me recall how, three different procedures to endow the shape space. So which is a quotient space of the, so here F is not a flag manifold as before, but a pre-shape space. S is a space of unparameterized shapes. So this shape space is a quotient space of the space of parameterized shape by the group, which in my case would be the group of reparameterization, but it is the same with translation or rotation or whatever you want, has a symmetry. So the classical quotient Riemannian metric is defined like this. So it's a classical Riemannian submersion theorem here. So you have this manifold F. The group is acting in a nice way. So in this case, the quotient space is a smooth manifold. And you have an invariant metric so a G invariant metric on the top space. And I added one condition, which is a splitting of the tangent space. This condition is for technical reason in infinite dimension, but actually can get rid of it. But for this presentation, I will stay with that. Your two conditions are the following ones. The Riemannian metric on the top space is invariant by the group action, which is exactly this. So if you act by an element of the group, the same element on both sides, on both vectors, then the value of the scalar product will not change. So that's the invariance condition. And I added this decomposition condition. So the kernel of P is a natural projection, a canonical projection on the quotient space. So this kernel is exactly the tangent space to the fiber of this fibration. And you take the orthogonal here for this Riemannian metric on the top space. And this will be a model for the tangent space downstairs. And so this Riemannian submersion theorem is a tautology, actually, because you're just restricting your Riemannian metric on this orthonormal complement to get a Riemannian metric downstairs. So the only condition of the invariance is just to make sense that this what you get is independent of the lift. So yeah, so that's a classical Riemannian submersion theorem. So that's the first way to endow a quotient space with a Riemannian metric if you have at hand G invariant metric on the top space. The second procedure is the following. You suppose that you have a smooth section of this fiber bundle. So, for instance, in the talk I presented before, arc length was a section of the parameterized curve by arc length is a smooth section of the fiber bundle composed of parameterized curves, modulo the group of this fiber bundle. So you have this fiber bundle, and you have a section, and then which is a smooth manifold of the ambient space. So you can just restrict your Riemannian metric, so the ambient Riemannian metric, to this smooth submanifold. And this is the content of a Riemannian immersion theorem. So given a smooth section, which may not exist for some fiber bundles, but as I said, I had an example with arc length where it is globally defined, and in application you can also work locally. Anyway, you have a smooth section and a Riemannian metric on the ambient space, and you just restrict it on this submanifold. So the inclusion is an isometry. And then this section gives you an isomorphism with a quotient space, and you decide that this isomorphism is an isometry. So that's how you build a Riemannian metric on the quotient space using a section. So of course the Riemannian metric that you get downstairs will heavily depends on the section that you're using. So if you take the section of arc length parameterized curve with a given ambient metric, the quotient, the metric that you will get downstairs will differ from the metric that you will get when you choose another parameterization, like curvature length parameterization. So it will heavily depend on the section, but you can also look at different section, and so it will make the Riemannian metric downstairs vary. So you can optimize also using this setting to find the best metric that is helpful for your application. So the third way to endow a quotient space with a Riemannian metric is the procedure that Johanna was using in her talk, which is called gauge invariance. So here you start with a Riemannian metric, a G invariant Riemannian metric upstairs, and instead of computing the quotient metric, which aim at computing the horizontal space, which is the orthogonal of the tangent space to the fiber, we select a preferred. So here, okay. Again, that's the setting where the tangent space splits. Usually, you have only a quotient space. The tangent space downstairs, the quotient space, as in the talk of Johanna. But let me restrict to the case where you have a splitting of the tangent space. So this is the tangent space of the fiber, and you have selected preferred complement, which for curve can be given by variations that are orthonormal to the curve, or for surfaces, variations that are orthogonal to the surface. So these are preferred complements. And so you can restrict the ambient top metric to this subbundle. And because this subbundle is a complement to the fiber, it will be isometric to the tangent space downstairs. And you use this projection to enter the space downstairs, the base, the quotient space, with the restriction of a Riemannian metric to a normal bundle. So this restriction has two properties. It has a kernel because what you do is instead of applying your metric on arbitrary tangent vector, you first project on the normal, and then you compute a metric there. So because there is this projection step, there is a kernel which is exactly the tangent space to the fiber. So in this setting, the tangent space to the fiber has zero cost, zero length. So it has a good properties in application where, for instance, perhaps I should say first, when you're developing an algorithm and you need, for instance, to reparameterize the curve in between two steps of the algorithm because your points are clustering or coming too close together, this is the right framework to use because reparameterization is zero cost. So you have the right at each step of your algorithm to reparameterize, and it will not change anything. It will not change the length of the curve. We will see an example later. For instance, for curves, so here again, a curve, so C1 are parameterized curve of length 1, A1 are arc length parameterized curve of A1, and you can project on arc lengths. So you have this section of arc lengths, which is a smooth manifold, diffeomorphic to the quotient. And you can consider, as in the talk of Viona, a two-parameter family of elastic metric on the space of parameterized curves. So there are two parameters, A and B, and there are bending and stretching component on this elastic metric. So the Riemannian submersion case, so the first procedure, you endow the quotient space downstairs by the quotient Riemannian metric, which is given by this formula. So you have a minimization step, or you compute the horizontal space of this metric and you restrict to horizontal variations. So this gives really better results. For instance, the last line here is the deformation that you get from the two ballerinas using this quotient elastic metric. So it's really smoother than the two procedure above. So you can also play with all the three different procedure and ask yourself, for instance, how does this quotient metric looks like on the manifold of arc length parameterized curve? And this is exactly what we did. I should have mentioned from the start, this is a joint work with Steve Preston from New York. And what we did in one of our paper is to express the quotient Riemannian metric of the elastic metric, but expressed on the manifold of arc lengths. So, as I said, this implies, so here you have to project on the tangent space of arc lengths, and we could compute this projection. So there is an equation here to be satisfied to compute numerically. We cannot do it. We cannot do it analytically, I think, in this case. Anyway, in order to to deform the curve and staying on arc lengths, and you want the geodesics to stay on the arc lengths and the metric to be given by the Gaussian metric, you have to solve this kind of equation. And yeah, perhaps I will skip this, but then you can do an analysis to see what are the best parameter A and B, which are included in this metric. I will skip this one because I think, yeah, so there are some properties that you should take into account. For instance, here you want to deform, there is a circle at the beginning and a circle at the end. You want to see how path threatening will behave. You put an ellipse in the middle, so this is the path that you start with, and you want to apply a gradient descent, for instance, to obtain the geodesic, which will be the constant circle along the time. And so you can analyze how the parameters are important in the numerics. And one of the things which is not good for numerics, for instance, here the gradient is really located at the middle shape, and very small gradient around. So this is really picky at this. So this is really not good. You need a smooth gradient to have better numerics. Otherwise, the shape in the middle deforms too much in comparison to the other shape in the path. Anyway, let's me go back to surfaces. In the case of surfaces, you can ask yourself if there also is an equivalent of arc lengths. So, is there globally defined sections of the fiber bundle of parametrized surfaces? Actually, there is one, but modulo PSL2C actually. So if you start with a genus 0 surface, this is a Riemann surface. So it's compact and simply connected. So there is a uniformization theorem that says that this Riemann surfaces. So here you see there is a complex structure actually at each tangent space, which is given by the rotation by 90 degrees. From complex analysis, we know that there is a conformal map from the unit sphere to this shape. This conformal map is almost unique. It's defined modulo the fixing of 3 points on your surface. So there is a PSL2C acting on it. So it's not completely unique, but modulo a finite dimensional group, it's unique. Compared to infinite dimensional parameterizations, that's really a good step. Anyway, there are algorithms to compute this kind of universalization maps using circle mapping. I haven't implemented them, and perhaps that's anyway not the best parameterization we want, because there is a lot of distortion or usually in this kind of parameterization. So the other point of view is to use the third method, a gauge invariant method, where you just forget about the fibers. You put zero cost there. And so this means in particular that if you have two different passes between surfaces and you lift them differently in the space of parametrized shapes, all the lifts will have the same length. Because there is no cost in the vertical direction, all the lifts have the same length, and this is a property that is called gauge invariance, because there is a group not only of a fixed reparametrization acting on each time of the deformation, but you can vary your group element with time. So this is a gauge group acting on the space of curve, and this gauge invariant metric is invariant by this bigger group of symmetries. So that's why, and in your numerics, if you start with a path downstairs and at some point you reparameterize it, you just jump in the fiber without any cost, and then you can continue your algorithm. And if you so upstairs the curve will have discontinuities, but downstairs it will stay continuous, and that's really a good thing to use in algorithm, and probably you used it already, for instance, for rescaling or for translation. If rescaling and translation have no cost, you can do this, and it will not affect. You will not affect the searching for geodesic, for instance. So that's the main point here. I think I will stop here. Thank you very much for your attention.
We have time for questions now. Does anybody have any questions for Barbara? If not, we can take.
What was the basis metric used in the examples in the last slide? I mean, before
the metric.
Before taking the quotient.
Yeah, so exactly the same elastic metric as Johanna's used in her talk. So I think I don't have for surfaces. You mean, or for? Yeah, so here I have the family of elastic metric on curve, and you have a family of elastic metric on surfaces. That was in the slide in the previous talk, but it's a very common used metric on surfaces, which is called elastic metric. The family, 3-parameter family of. So, yeah, I'm sorry I don't have it here. Because the point of this talk was to be very general, so you can choose any metric you want with a property that is invariant by the group you're interested in, and that's the main message. So pick the one you like. Actually, yes. So perhaps I should refer. So to this paper with my collaborator Dria and Daudi and Srivastava, where we do this with the elastic metric on surfaces. Okay, yeah, and yeah, the same idea in notices of AMS. Yeah. Other questions?
Any other questions? No? Thank you, Barbara, for the talk.